Hi everyone, let's get started on actually using the substitution rule now. So the substitution rule is basically a trick to help us more easily work our way backwards out of chain rules. A lot of the time you can guess and check yourself out of chain rules, but sometimes it gets a little tricky and hard to spot, and this just gives us a nice way to hide some of that mess. So the idea here is if you start with something like this that looks like it came from the chain rule, and you can spot that you have a g of x and a g prime of x floating around, we can do some substitution to hide these. I'm going to go ahead and switch this to w as well. I'm on a mission to make them all w's. I need to remember to change them in my notes. So you would replace the g of x with a w, which would then mean that you would need to replace the g prime of x dx with a dw. And that's how it turns into the integral of f of w dw. So there's actual nice step-by-step to make this happen, but that's what we're trying to do. If you can spot the g and the g prime, you can just substitute them out by replacing them with a variable. Okay, so if we're looking at these, the big thing is trying to spot the w and the dw. So there's a couple of things you can look for. One is you need to, if you see some kind of function floating around, the only way it could be your w is if its derivative is also floating around, or something that is really close to its derivative and is only missing a constant. The other thing is that we're looking for composition, right? The goal is to actually isolate this f function. So you're looking for somewhere that your g function got plugged into your f function. So what I'm seeing is the composition is kind of showing up in the bottom for me. I have something raised to the third, or you could think about it as the negative third since it's in the bottom. So that's something that jumps out at me. The other thing that I like that's confirming that that might be a good place to focus is that if I look at this as the inner part, its derivative would be 2y, and I have that y floating around. So what we're going to do is we're going to say, okay, I suspect that my w should be equal to y squared plus 4. If that is true, then you should be able to take the derivative dw dx, and you get, oh, hold on, I'm completely lying to you, dw dy, and you get 2y. And here's the part that's a little new for us, not completely new I don't think, but a little new. We're going to manipulate this statement a little bit. If we're thinking about dw as some infinitely small change in w and dy as some infinitely small change in y, then we can do a little bit of manipulation here, pretty much like fractions work, and we won't be wrong. It seems a little funny, but it does work. So I'm going to rearrange in this way. I'm going to multiply by the dy, and what I'm trying to do is give myself somewhere else I can substitute. So I get to substitute this out. I also need to substitute the dy out. And while I'm at it, I can certainly try to substitute the y out as well. That's what I really want to happen. So the only thing I'm not liking right now is I don't have a 2 that I can pull out. So I'm going to divide by that 2. And then you just need to take these statements really, really literally. So I am saying that y squared plus 4 is exactly the same as w. So I can replace that in the bottom. I am also saying that y dy down here is exactly the same as dw over 2, so I can replace that y dy by dw over 2. Don't forget that that w cubed doesn't get to come out of the denominator just because we've substituted out the numerator. And this is beautiful. This is something I can now integrate, so I'm going to snag the 1/2 out in front because it's looking a little weird. And what I really have is a dw over w cubed. It's completely fine to leave the dw at the end or move it up into the top of the fraction. Again, we can manipulate these. We're thinking about them as infinitely skinny widths of rectangles, so we should be able to do some fraction manipulation with those. Okay, so really important, the next step, the integration, the antiderivative, can only happen if all of your variables are matching up. So we kind of brought this up in, which section was that, 1.8? The variable kind of doesn't matter as long as they all match. So you could take a function or an integral and switch all the x's to y's and it would mean the same thing. But if you've got some mix of x's and y's, that's not great. And here we have to be really careful because we're replacing y's with w's, but it's not just y, it's y squared plus 4. So there's kind of a chain reaction that happens there. Chain rule, chain reaction, I like it. And that does affect things like what are we going to call the width of a rectangle and so on. So we have to very carefully replace not only the y's but the dy's. And we have to make sure that all of the y's have switched to w's. Once we do that, we're just looking at, now that I wrote it that way, w to the negative 3 dw, which means we're going to get a 1/2, we're going to bump that up, w to the negative 2, we're going to divide by the new power, plus c, and we're going to say we have negative 1/4, so I'm going to put the w in the bottom, negative 1/4w squared plus c. Okay, we integrated, this is fantastic, a lot of people are like, yay, done, party. If you quit here, you're still wrong. So the deal is we haven't made a mistake, so maybe I shouldn't say you're wrong, but you're definitely not finished. We haven't made a mistake. It's true that what we've written down is equal to what we've started with, but the directions were to actually find the antiderivative, and we haven't because the antiderivative of what we started with has to be a function of y. So the last step is just to substitute back in the y's. We know that w is exactly the same as y squared plus 4, so now that we're all done, let's go ahead and substitute that back in. Now we're done. Now we have found the antiderivative of this function.